see. Firstly, so the homework assignment is due a week from today, and as I said, they will henceforth be they will be distributed on Tuesday, and then okay, and then we'll have a few days, and we'll have a problem session, and then there'll be the TA office hours, so there'll be hopefully enough time and assistance if you so desire. Okay. All right. So let's see. Last time, we were reviewing the ideas of qubits, which are two-level quantum systems. That is to say, any quantum system where we can isolate two orthogonal states, we can call that a qubit, and people do. That the story of the qubit is intimately related to the story of spin angular momentum, particularly spin 1/2. Okay, so just as quickly review, we can think about the angular momentum vector operator with spin components Sx, Sy, Sz, which satisfy certain commutation relations, and we define these complex or non-Hermitian operators S plus and S minus as Sx plus or minus Isy, and the standard basis for that we typically write when we're thinking about angular momentum are the joint states that are joint eigenvalues of the magnitude squared and one projection of angular momentum. Typically, the z-axis is called the standard quantization axis, and with these eigenvalues associated with them. And the S plus and S minus play the role of the so-called ladder operators, or raising and lowering operators, that raise me and lower me along different projections of angular momentum along the z-axis in integer units, okay? And m ranges from a maximum value of s to a minimum value of minus s in integer units, so that there are two s plus 1 different orthogonal projections of angular momentum, okay? Along some direction. And particularly for spin 1/2, then this quantum number, the magnitude quantum number that appears in this s times s plus 1 is a half. That's what we mean by spin 1/2. And that means that there are two possible basis states, orthogonal basis states, which are, well, spin up and spin down, corresponding to the projection plus 1/2 and minus 1/2 along the quantization axis. And it's convenient to get rid of all these halves and h bars and define a vector of operators that are called the Pauli operators, factoring out the h bar over 2. We also define, it's a little bit annoying to keep track of this, sigma plus and sigma minus don't have the factor of 2. They're just Sx plus Isy without the factor of 2. So it's got a factor of 2 in the way the sigmas are defined. You got to keep track of that. You got to remember that. That's just how it is. The reason is because then, when we do that, we don't have any of these other square root factors around when we do the raising and lowering operator. That's why it's done that way. And so the Pauli operator satisfies certain relationships. This is just a rescaling of this with the factors of 2, and the h bar is gone. And the Pauli satisfy also an anti-commutation relation, which put together can mean that we have a simple expression for how to multiply any two Pauli operators together. When we multiply them together, if they're different, then it gives me another Pauli operator with a factor of I that's plus or minus 1, depending on the cyclic permutation of I, J, and K. So, for example, Pauli X times Pauli Y is I times Pauli Z, and cyclic permutations thereof. Moreover, the Pauli operators all squared of the identity. Okay, so sigma Z squared is 1, sigma X squared is 1, etc., etc. And so we can write them out, the operators written in terms of these basis vectors. So the raising operator, you see, takes spin down to spin up with no factors or square roots there. So that's why the twos are defined the way they are. And as a basis, as a matrix in the Z basis, sigma plus takes this form, sigma minus takes that form, and sigma x, which is sigma plus plus sigma minus, takes that form. Sigma y, which is sigma plus minus sigma minus over I, takes this form. And sigma z, which has its eigenvectors spin up and spin down with eigenvalues plus or minus 1, takes this form. Okay? And those are the Pauli matrices. Yes?
Is there notation defined to say that x and y are just the real and imaginary parts of the...
Right. I mean, more precisely, they're the matrix generalizations thereof. Okay. So we would call it the Hermitian part and the anti-Hermitian part, because the complex conjugate is the dagger. So if the moral equivalence of a real number of a matrix is a Hermitian matrix. The moral equivalent of a pure imaginary is an anti-Hermitian factor. So when you take the star, you get minus it. Yeah.
The Pauli Z is basically the projector of a mixed state of up and down.
No, because it's got this minus sign.
Isn't that still?
No, because a statistical mixture is a convex combination with positive probability.
Gotcha.
So this is not like a density matrix. Okay? Yeah. Nate, yeah.
I've sometimes seen that instead of having a sigma minus, they have just the Hermitian conjugate of the plus. Is that
Same thing. This is, of course, true that this operator is the Hermitian conjugate of this. You see that because that flips the Braun cat. You also see it because that's what you get when you take the transpose conjugate. So the fact that this matrix is the transpose conjugate of this means that this is the Hermitian conjugate of that. And that's kind of as Donald was reminding us. Of course, I didn't do this right. So the conjugate of sigma plus is a Hermitian conjugate. This is this, and then I change the minus side, so you see that sigma plus goes to sigma minus. Yeah.
Is that a bit of a generalization for ladder operators in the sense that like whatever my raising operator is, the lowering operator has to be the Hermitian?
Yeah, I mean, this is a longer discussion. The relationship of ladder operators in general has a certain algebraic structure, and it can be looked at in terms of differential equations and the Sturm-Liouville theory, but there's only so much digressing for now, so let's continue. All right, so one of the things we also were saying, I said that the set, I'll call it sigma alpha, where alpha is 0, 1, 2, or 3, where this we typically call sigma 1, this we call sigma 2, and this we call sigma 3, and sigma 0 is the identity. Now the identity is closer to thinking about something that looks like a density operator. But it's an unnormalized density operator because the trace should be 1 and the trace of this is 2. If they're divided by 2, then the identity over 2 is the completely mixed state, okay? All right, but I digress again. So this set, I would say, forms an operator basis. The notion of an operator, we think about a basis, we typically think about a vector space. A vector space, whether it's real three-dimensional space or complex two-dimensional space, we can think about a basis of the vector space. What does it mean to talk about an operator basis? I want to introduce this concept if you haven't seen it before, because we're going to see it throughout the year in different contexts. Okay, so let me just say just a very few quick things. Okay, so D by D matrices, let's call it M, form a vector space. The space of matrices themselves are themselves, I can think about the matrices as vectors. What does it mean to say this? What counts, in what way would we say that this set of objects is a vector space? What properties must it have? Yes, Ben?
They must span some set of other arbitrary matrices.
Well, that's about a basis. Okay, so this is a little more, just even before, what does it mean to say that a set of objects forms a vector space?
You can combine it with one for any other argument?
Yeah, so, yeah, so the key idea is linear combination or superposition with some scalars, some scalar field, whether it's the complex numbers, the real numbers, or some other more fancy field. But I can think about, if I have two matrices, if I can add them together and they form some other matrix in the space, then it's a vector space. Okay, it also has to have something which we would call the null, so I have to have the zero matrix that when I add to it, and I can have the identity. So it's clear these things is a vector space. And in fact, one way to think about it very simply is that I can map, let's just say I had the matrix elements here. This is an example of a 2 by 2 matrix. I can vectorize this by just stacking the columns on top of one another. So I've turned the matrix into something that looks more like a vector in our head, but it's the same thing. I've just rearranged it. But I can think about this as a vector, okay? So what is the dimension of this vector space? If I have a D by D matrix, what is the dimension? In this case, 4 and general for D? D squared, right? They're D squared linearly independent vectors, okay? And I can think about a basis which might be vectorized, but back in the original, it's this, and this is what you might call the standard basis. No, I'm not talking about SU2 right now, that's about groups. This is the standard basis of 2 by 2 matrices. Okay? Yeah?
What do you do?
Oh, why did I just do that? Okay. Yes?
This is a bit of a new term to me, so I'm trying to, when you do this sort of mapping, is this almost like looking at like a, what they call a symplectic form?
Symplectic form?
Yeah.
No, I think that's a fancier thing.
Uh-huh.
This is just, I've just relabeled the indices.
Okay.
It's nothing more than that.
I see.
Yeah.
I see. Thank you.
So now I can also think about, we always think about a matrix as a representation of an operator in respect to a basis. So I can also not just think about matrices as a vector space, I can think about the operators as a vector space. So an operator on a d-dimensional Hilbert space is a d squared dimensional operator space. The space of operators themselves, the set of all operators that act on the d-dimensional vector space is themselves a d squared dimensional vector space, okay? So I can think about an operator basis So let's just say if I have a d-dimensional vector space, let's just say I have some basis for it. Okay, that's a basis of the vector space. And I want to think about what is a basis for this? Well, one way to do it is just take because as you could see, I could write M if I just put in a complete set. Let's find it IJ. Doesn't really matter, but I comes before J, it comes before elemental P. So you see that I can call these guys, these outer products, as a basis of operators, such that this operator is a linear combination of these basis operators weighted by coefficients. And those weightings are the matrix elements. And you can kind of see that there's lots of different representations you go between these, clearly with a 1 and zeros everywhere else, that's a basis of matrices. If I just multiply it by the appropriate matrix element that goes in that spot, that's a way of decomposing the matrix into this amount of that basis matrix, this amount of that basis matrix, et cetera, et cetera. Don, another question.
Yeah, were there, I might have missed it, were there any constraints you placed on the operators?
Nothing. It's a linear operator.
Okay,
Whenever I say operator, I always mean a linear operator.
okay.
Okay? Yes, Tristan.
So, if,
I don't think I think it's too far off.
Okay, we'll come back. Okay. So, there's another aspect of this, which is we can have a structure on a vector space that gives it an inner product. The notion of length we impose in some way on top of our vector space. So I can have an inner product. So for example, if I have a vector in my two-dimensional vector space, which is that, then I can find the expansion coefficients by the projection, the inner product between those two, right? And so that gives me, in general, if I had two vectors, if I had psi and I have, say, phi, which is some superposition with some other coefficients, then the inner product between these two guys, based on this, is the sum like that. we can look at that also in terms of matrix multiplication with column vectors and row vectors and the like, okay? So this is sometimes called, tells us that the norm of the vector is the sum of the squares of this. And so the norm of the vector is the square root of this. So we can call this the Euclidean norm, because go Pythagoras. That's what we're doing, right? So similarly, I can talk about a operator space inner product. And I can do that by borrowing the Cartesian or Euclidean inner product in the vectorized form. If I just turn the matrix into a big vector and then take an inner product between those two vectors in exactly this way, that's a particular operation on the matrices. And sometimes we use curvy brackets to, instead of a square one for this. So I can think about the inner product between two operators as the trace of n dagger n. That's, I don't know, maybe it has some other fancy name. I hate these fancy names because I never know. They're named after someone, and it just means you know it. Let's say Hilbert Schmidt, you know, or for beanies or whatever. It's, you know, somebody's fancy name. It means I'm in the club, you're not. That's the Hilbert Schmidt inner product, and it's basically the Euclidean inner product. I challenge you to show that when you take this trace, it's equivalent to looking at n1 star, n2 1 star, n2, n1 2 star, n2 2 star times this. Right? That's the vectorized version of that. And when you take that inner product, it is this. Okay? So, and we can sort of then see, for example, this is an orthogonal basis. If you take the trace inner product between two of these for different indices, I and j, you'll get 0. Because they're really the vectorized version of the standard basis. Right? And so, let me just complete this thought, I'll take questions. So Mij, how would we find it? Well, we would look at just like we did for the Hilbert space of vectors, now I have the Hilbert space of operators. Now, this dagger means I changed the bra and the cat. Everyone see what I just did? I replaced the dagger by the flipping of the bra and the cat. And how do you take that trace, my friends? That's right, it's the click rule, which means this is equal to so that gives you the matrix element, right? That's the matrix element is the projection of this operator onto this basis operator. It's another way of thinking about it. This is another mathematical way of doing the same thing. Yes, ma'am.
Maybe I'm not understanding how you take the matrix and turn it into a single vector, but why is it n2 1 star, then n1 2 star, and not n1 2 star, and?
Because the way I happen to choose the stacking, that's just a choice. It's just the rows and columns, so I stacked it with this and then stacked it like that.
But if you take the complex conjugate,
Then I take this and I star it.
sorry, formation conjugate.
Yeah, I put this on its side. So it's in that order. It takes it's just the transpose vectors. Yes?
But since now, after especially we found EI and EJ to be orthonormal to, or orthogonal with respect to each other, am I gonna get a Kronecker delta out of that?
I get a Kronecker delta if I took the inner product between two different basis vectors. But this is not orthogonal to that necessarily unless this happened to be 0.
Sure.
This just projects me onto that. Yes?
A little bit. Let me see if I just understand this right.
Uh-huh.
So the weighted outer product is the operator space of the
That's
vector
right.
space.
Mm-hmm.
Now, the weighting on the outside there, is that the same operator that we're doing the inner product on the inside on the right? Like the M and M? Or is
So
that?
the MIJs are matrix elements.
Okay.
So they are numbers. They are the elements of this matrix.
So they're not representing an operator itself then?
The operator, there's 3 things we're talking about.
Okay.
The operator, the matrix elements. Okay? The matrix is a representation of the operator. The operator is an abstract thing that says, take this vector to that vector. It's a map between them. So the matrix is a representation, it's like a coordinate representation. And the coordinates are the elements of the matrix, and they're all interrelated in this way. Okay, with that said, again, the set, I'm going to continue here. Form an orthogonal operator basis for operators on 2D Hilbert space. This is not the standard basis. The standard basis would be the outer product between the spin-ups and spin-downs, right? This is a different basis, but they are just linear combinations of the, right? I mean, this guy is a linear combination of one of the basis vectors and another. This is also, and if I take these guys in linear combination, I get this basis, which is to say that any operator that acts on this can always be written as some amount of the identity, some amount of sigma x, some amount of sigma y, and some amount of sigma z. Doesn't matter what that operator is, any linear operator that acts on a 2D can be written this way. And often we'll write it as the vector A dotted into the vector of operators. Oh my God, so many notations, okay? So how do I find these coefficients, A0, AX, also known as A1, A2, and A3? How would I find them? I need to project onto then. I said they're orthogonal. I didn't say they were orthonormal. So let us look at the trace inner product between any 2 of these, alpha and beta, where alpha and beta can be. Okay, so firstly, I'll look at, this is the inner product between 2 of these guys, which I have to do that, where these go to 0, 1, 2, or 3. meaning the identity, sigma x, sigma y, sigma z. And I want to take that trace inner product, which I have to, this is Hermitian, so every one of the Pauli's and the identity is Hermitian, so I don't have to worry about that. And what is the trace of this? Well, we can look at something that was covered up. We have this lovely relationship here, right? And if this is, so firstly, let's say that, let's look at the case where alpha is 0, okay? If alpha or beta is 0, so then I get trace of beta or trace of sigma alpha. What is that trace? 0.
Yeah.
And if neither of them are 0, then alpha is I or j, and I can look at the trace of sigma I with sigma j, and what is that? Well, it's the trace of sigma k, which is 0, delta ij times the tracing of the identity, which is 2. So what we have thus is that the inner product between two of the Pauli's is equal to twice that. So they're not orthonormal, but they're orthogonal. We could normalize them by dividing by 1 over square root of 2, but we never do that. So it's actually more convenient to rewrite this like this. Get rid of that factor of 2 and define as the projection of the operator A onto the Pauli. Okay? So the expansion coefficient A0 is the trace of the operator, and the vector A is the trace of the operator with the vector of Pauli's. Everyone clear on that?
Where was the factor 2 you mentioned getting rid of?
I divided, the fact that this thing was 2, I divided everything by a factor of 2 here.
Okay.
So that when I take the trace of this, A0 is this. That 2 in the denominator cancels the 2 in the numerator. Okay. This is really important to remember. You will use this all the time. And if you haven't to this day, you should from now on. Because we're going to show you all the tricks of how you deal with 2x2 matrices by just expressing them in terms of the Pauli's. Okay? You will never diagonalize a 2x2 matrix again with taking the determinant and the secular equation. Never in your life should you ever do that. You should just know how to do it by eye using the Pauli's as we will see. Okay? All right. So, very good. So with that said, I can, for example, consider the density operator, also known as the quantum state of spin 1/2, or a qubit. Okay? The density operator is an example of an operator, a linear operator on a 2D Hilbert space. And because it is, I can express it in this way. I can express rho as a half times the trace of rho times the identity plus a half the trace of rho with the vector of Pauli's dotted into that. That's just an example, that was for some arbitrary for A, now it's specific for the density operator. What is the trace of rho if this is a normalized state? 1. And we define this vector, this is a vector, because it's trace of rho with sigma x, trace of rho with sigma y, trace of rho with sigma z. And that vector of numbers I'll call Q. And that trace of those vectors is called the Bloch vector. We'll come back to this, remind ourselves about this. So for the density operator can be written as 1/2 the identity plus Q dotted into C, where Q is the trace of rho with the vector powers. It's a very useful representation of the density matrix, as we will discuss right now. Yeah?
For the A vector, we have an operator left multiplying the vector operator.
Yeah, so let me unpack this horrible notation. This is a shorthand for 3 coefficients, AX, AY, and AZ. AX is the trace of the operator with sigma x. AY is the trace of the operator with sigma y. AZ is the trace of the operator with sigma z. So there are 3 components of this vector. Each component is the operator traced with the power along the different directions. When I write it this way, this is a vector as opposed to a vector operator. A vector operator is a vector of operators. It's like the position vector operator or the angular momentum vector operator. All right, let's continue. So let's think about this. We're going to come back to this. Let's think about pure states. Let's say, for example, spin up along Z. Rho is this. But it can also be expressed as this, because any operator, the density in particular, normalized, is some amount of identity, which is a half, and then this. So how can I do that? Well, I can take the trace, but I can just also, in this case, just kind of look at it. If I come back over here, if I add sigma z to the identity, add these two together, I get twice spin up along this. So this operator is actually 1/2 the identity of sigma z. Everyone see that? Add those two operators together, you get the projector along the z-axis. So what's the Bloch vector in this case? If it has to have this form. What's Q here?
0, 0, 1.
What is the vector? I want the vector, not its coordinates. It's the vector along the z-axis. It's the unit vector along the z-axis. So for this case, Q is just the vector along the z-axis, and it's the unit vector, right? Because it has 1 there. Everyone see that? What if I had spin down along y? Well, I challenge you to show that that is trivially, Well, let's do first, let's take one step at a time. What's this? If you look at this, if I take the identity and I subtract this, I get twice spin down along y. So this is equal to this. What is the block vector here? It's the
Minus
unit
z,
vector
yeah.
pointing in the minus
Minus
direction.
z,
Yes.
yeah.
Okay? And just because it doesn't matter what's x, y, or z, etc. Right? Because if I wrote the operator sigma y, it would be up y, minus down y, and then do the same algebra, I get this. So I see for all of these cases, and in general, if I have spin up along any direction, I can always write this as that, where n, sigma n, is the unit vector dotted into the vector of Pauli's. So this is an interesting way of writing a projector into D Hilbert space. And what is the Bloch vector for this pure state? E sub n.
Yes,
It's the
it's sub n dotted into sub n. Yes,
It's the
exactly.
unit vector along the direction E sub n. Yes?
Now, when I write it in that form, doesn't that give me some insight of the purity of the density matrix?
Yeah,
Like,
we'll
not-
get there. Absolutely, it sure does, but give me just
Take your time.
5 minutes and we'll get to that point. All right, so we have some interesting things that we just learned, or maybe reviewed. Consider an arbitrary pure state of spin 1/2, also known as the pure state of a qubit. What we all learned from the homework that we just did is that every such state is equivalent to spin up along some direction. Right? So if I have a sphere in 3D, x, y, z, and I have some direction in space, that is specified by a unit vector on a unit sphere, every pure state is in one-to-one correspondence with some direction on the sphere. Okay? So if I have a direction on the sphere, which is some amount of projection on the z-axis, and then some amount of projection on the equator with an x and a y component, then that state, that direction in space corresponds to some spin along that direction. And what is, if I want to write that in terms of a superposition of the standard basis, spin up along z and spin down along z, what are those coefficients given this direction? So this is some amount of spin up along z and some amount of spin down along Z, because every pure state is a superposition of the basis states, right? And we learned how to parameterize that. What are those? Cosine theta over 2.
Plus E5.
Now, this is up to overall phase. This is the convention we will choose, right? So, and spin down along Z is so there's a one-to-one correspondence between directions on a unit sphere, directions in space, and pure states of a qubit, okay? And so we do a one-to-one correspondence of this with the sphere where that direction now corresponds to this state. And what is this correspondence? This is the Bloch vector. This vector, we just said, for any pure state, it is defined by its Bloch vector. For a pure state, it's a unit vector. It's a vector of magnitude 1. And this space is known as the Bloch-sphere. And the surface of the Bloch-sphere represents the set of all pure states of the qubit. Because all states of the qubit are in one-to-one correspondence with directions in space. And that direction is the Bloch vector. Meaning I can also write the state as a density matrix in this manner. Okay? Any questions about that? Now, this is a point I think Tristan brought up maybe at the problem session, I don't remember, it was last lecture, which is that there's something to be very careful about here. This is actual, what I've drawn here with my horrible potato-like sphere, slightly misshapen, is directions in physical space, okay? This direction, that direction, that direction. And in principle, I can prepare a spin, say with a Sturm-Gerlach apparatus that would be, to the degree I could do it in the lab, really pointing in that direction in space. And directions in space have their own orthogonality. X is perpendicular to Y is perpendicular to Z in R3. But this is a mapping of the surface of the sphere embedded in R3 onto a Hilbert space in 2D with complex coefficients. And what is the state that is orthogonal to this state? It's the antipode. Things on opposite sides of the sphere are orthogonal in Hilbert space. Spin up along Z is orthogonal to spin down along Z. That was somewhere maybe just erased when we had the SM sub S vectors. So the thing that was all the different projections on Hilbert space are orthogonal in Hilbert space. Okay. So it's embedding a mapping, but it's mathematically not the same thing. Okay. So how would I calculate? Here's a great thing. Suppose I have two pure states that are corresponding to spin up along two different directions, or it could be n, could equal to n prime. And I want to know what is, they correspond to E sub n and E sub n prime. They're two different Bloch vectors. the block vectors define the point in the direction in space and identify the spin direction. And I want to know what is the inner product, let's say square. What is the overlap, the probability of finding this state if I prepared this state? Here's a cool trick. You ready? So I can write this inner product as actually the trace inner product between that projector and that projector. Right? Because with a star, did you do it in your head? Do you see it? Some nods. Okay. But what is this? Well, this is the density operator associated with the state n prime, and this is the density operator associated with the state n, right? And we know that we can write the density operator in terms of its block vector. So we're going to write this guy as the trace of 1 plus sigma n prime over 2 times the identity plus sigma n over 2. You with me? And so let's write out all 4 terms. We have, I'm going to take this outside a quarter. I have the trace of the identity plus sigma n plus sigma n prime plus sigma n sigma n prime. Okay? So how do I take that trace? The trace of the identity is 2. The trace of the sigma is 0 because they have plus and minus 1. The trace of the sigma, this guy's 0. And now I need to find the trace of this. This is going to be a little bit tricky. But here's the trick. The trace of these 2 Paulis along arbitrary directions is equal to the trace of E sub n dotted, or E sub n prime dotted to that, times E sub n dotted to the Paulis. Okay? That's what I mean by this is you dot the direction into the vector of Paulis, which I can write as the sum over I and j, the trace So I just wrote out the Paulis as, you know, some amount along each of the directions, okay? Summed over the components. So I just wrote out this vector as a sum of the Pauli I in the direction I. That's what I did. And this guy, I wrote J, and then I wrote that. Everyone clear? There's so many things. There's vectors and matrices and vectors that have matrices and that, right?
You do it that way because once we have that in terms of the Paulis, it's super easy to trace.
Yeah, so what is this trace? Well, it's got the Kronecker delta, right? This was equal to I epsilon I k sigma k plus the identity times delta ij. And I take the trace of that, the trace of this is 0, and the trace of this is, of the identity.
That's
So
two going by the
is
ID.
EIJK traceless? Or
That's a different, I'm tracing over the this is the things in Hilbert space.
Oh, okay.
Yeah, that's a very good question. Yep. So this is equal, I mean, we had this, what we just said, you know, we wrote it somewhere over there. There it is. The trace of sigma I times sigma j is 2 delta ij. So putting that all together, we have that the inner product between these two vectors squared is equal to 1/2 1 plus en dot en prime. Oh, I love that expression, it's one of my favorites. It's so cool. Notice the difference, this is about the inner product of the vectors in Hilbert space. This is about the inner product of the directions in 3D space. But there is this relationship thereof, okay? Notice that if En equals En prime, then this inner product, as expected, is 1. But if En equals minus En prime, meaning the antipode, the thing that's in the opposite direction, then this is 0. Things on the antipodes are 0. And more generally, if I think about these two vectors, the vectors on the sphere, there's some angle between them. I'll call it capital theta n prime. Now I can't ever resist telling this story because every time I write this, it makes me laugh. When I was a grad student, there was a book in nonlinear optics by Ron Shen. And God knows when this book was written, probably was written in the 1970s, maybe the 80s, before they had LaTeX and typesetting. And you know, I'm sure that what Ron did is he wrote his notes by hand and then gave it to the copywriter, and you know, they would print it. And if you're out there, there were these things that looked like this. That's how it looked, and we used to call it the Circle H Ranch, because we had no idea what this was, but it was clearly supposed to be capital theta, and the guy didn't know, so they created this whole thing, and they had to craft the book this way. All right, only halfway. But, all right, so what's the point? The point is that I probably have, you can come to my office, I probably still have the book. So this is that expression, right? Where circle H is the angle between the two directions in physical space, okay? Which, if you remember some of your trig identities, this is the cosine squared of the half angle. Mm-hmm. You know, at 100, it's so great. So that's the geometry, right? So if it's the half angle that determines the things that are at 180 degrees in spin up and spin down, or are orthogonal in Hilbert space. Things that are at 90 degrees, that would be pi over 2. This would be cosine of pi over 4, which is 1 over root 2 squared of that as a half. So if you have something, a spin up along the x, along z, and spin up along x, there's a 50% overlap. Okay. Yes.
So, does this also, I noticed when you extended out the first step from the Brockette squared and then into the trace of the.
Yeah.
That trace of the two density matrices would have been the same as our.
That's right.
Hilbert-Schmidt inner product.
That's right.
Does this all still work if you're in mixed states?
It does. So, that is for sure true. So, let's talk about mixed states now. And comes to the other question we're coming about purity. So now let's go at an arbitrary state, pure or mixed. Okay. So let's think about, well, firstly, the trace of rho is 1, that's here. But the purity of the state, we said, was the trace of rho squared. And using exactly the same algebra as you suggested, what is the answer to that?
Let's do 1.
No, it is if it's a pure state, but the general form of that would be related to the inner product there, right? Which would be 1/2, 1 plus the magnitude of q squared. Because the inner product between the two states would be 1 plus the dot product between q and q prime. So, what does this tell me? We know for spin 1/2, the purity, what's the maximum value it could be? 1
It's bounded by
for a
0.
pure state. And what's the minimum it could be?
0.
It's not 0, it's a very thing, it's good to keep, it's the purity is when I have the completely mixed state. If I have a completely mixed state, I have a half of up and a half of down, and the trace of that squared is a quarter plus a quarter, which is a half. So in this case, what is, if the trace of rho squared, this tells me that the magnitude of q squared is the trace of rho squared minus 1, I'm sorry, 2 times that minus 1. Right? So for a pure state, what is the magnitude of the Bloch vector? 1.
Okay.
Because trace of rho squared is 1, 2 minus 1 is 1. And for a completely mixed state, what is the magnitude of q? 0. Because the trace
Yeah,
of rho
it's 1 minus
squared
1,
in
that's
that
0.
case, we just said it was a half. 2 times a half is 1, minus 1 is 0. So, what we thus have now, we go from the Bloch-sphere to the Bloch ball. Often called the Bloch-sphere, but it really isn't called the Bloch ball, because the sphere is only the surface of the ball. The ball, in my slightly misshapen, you could do better. So, if I'm on the surface of the sphere, these are pure states. The states inside the ball are the mixed states. They are the states that don't have purity, but they might have some polarization because their magnitude doesn't have to be exactly 0. It could be something that's between 0 and 1. So it could be polarized more in one direction than the other. It might be 4/5 up along Z and 1/5 down along Z, it's mostly more up along Z than down along Z. Its Bloch vector would be along the Z-axis, but it wouldn't be magnitude. It would have a smaller magnitude. So that state is pure, this state is mixed. And the origin is the completely mixed state. The completely mixed state is not polarized in any direction at all. It's just completely random state. And all quantum states of a qubit are points in the Bloch ball. Okay? The surface of the Bloch ball, the Bloch-sphere, are the pure states. They're parameterized by 2 parameters. The mixed states have 3 parameters, because not only the direction, but the magnitude. Okay? Very good. What was I going to say? Maybe there was something I forgot, but we'll just leave it there. All right. Very good. Yes?
So this 1/2 q dot in the sigma vector, this is strongly dependent upon how I prepared my state.
No. This representation is absolutely general. No matter how I prepared my state, yeah. But the
Right.
value of q.
That's what I mean, when it comes
The
out.
value of q depends on the state preparation. If I prepared it with 0 noise, it would be a pure state. Q would have magnitude 1 along some direction. If I had a super duper uber Stern-Gerlach apparatus that really could separate out those 2 beams, and there was no stray magnetic fields around, I would create something that would well approximate a pure state. So the value of Q absolutely depends on the preparation.
Thank you.
Yeah. All right. So I want to, in the last 10 minutes, talk about now dynamics. Okay. So we've talked about states and measurements, but we haven't talked about dynamics. Dynamics is what happens in the system due to the laws of physics when we're not measuring it. Okay? So and I'm going to qualify this by saying it's a closed system, meaning I have complete description of all the degrees of freedom. Completely closed, there's no friction, there's no outside effects, I know everything. So if I have that, I got the Schrodinger equation. And the Schrodinger equation says for a pure state, the equation of motion for the state as a function of time is that it is evolved according to the Hamiltonian. And the solution to this equation, assuming the Hamiltonian itself doesn't have any explicit time dependence, okay? So we can have explicit time dependence in the Hamiltonian when, for example, the Hamiltonian is parameterized by some classical field, like, I might have a magnetic field that's changing as a function of time, and if I treat that magnetic field as a classical field, then I'd have a time-dependent Hamiltonian. We'll come back to that. That one's messy. But if it's a time-independent, then the solution to this equation, we know, is a unitary map generated by the Hamiltonian. So now, if I started with a preparation that wasn't pure, but it evolved in time due to the interactions that are present, that is closed, there's no further noise in the problem, we can ask, how does the density operator evolve? Okay? The density operator, let's say if we started with a pure state, so let's say then the density operator would stay pure if I had a closed system. And I can now write down an equation of motion for the density operator rather than an equation of motion for the ket. So the rate of change of the rho of t is d by dt of the ket times the bra plus the ket times d by dt of the bra using the product rule. This is minus I over h bar h psi. What is this? Well, it's the bra of that. So it's plus I over h bar bra h dagger, but h is remission. Hamiltonian is remission. So what does this equal? Well, this is equal to minus I over h bar h times rho plus I over h bar rho times h, which is the commutator. So this is equal to minus I over h bar h commuted with rho, which is just another form of the Schrodinger equation. It's just the Schrodinger equation written in terms of the density operator rather than in terms of the state vector. It's no different. But the first person who wrote it down this way was John von Neumann. So this is sometimes known as the von Neumann equation. Oh my God. But it's really the Schrodinger equation just written in terms of that. And the solution to this says that rho of t is u of t times rho of 0 u dagger. That just comes by taking this and writing this with its dagger. Right? You take this and this, you get that. That is the solution to the Schrodinger equation. This looks like the Heisenberg picture, but it's not. It's the Schrodinger picture. What is the Heisenberg picture? If I have an operator observable at time 0 and I want to know how it evolves in time, in the Heisenberg picture, then dA dt is what? Yes, right. It's in the other order. It's got the other order. This is the Schrodinger picture, not the Heisenberg picture. Except that the state is an operator, but it's still the state. Okay. All right, so I just want to just make one preview in the next grace period, 2 minutes. So let's just say something about spin 1/2. have an arbitrary Hamiltonian. H. H is an arbitrary Hamiltonian unit. It's Hermitian operator that acts on the Hilbert space of a two-dimensional Hilbert space first and one half. What can we say about such operators? Generally, those operators can be expanded in the Paulis, because any operator can be expanded in the Paulis. So this is some amount, I'll call it A0 of the identity, and some amount with a vector of coefficients of the Paulis. I don't care what the Hamiltonian is, I don't care what the qubit is, it has this form, because every operator can be expanded in this way. It doesn't matter what the operator is. Everyone with me?
Wait, but if it's arbitrary, that means it can be like time dependent. So if B has to be.
Well, I could have time dependence. These could be time dependent coefficients if I want. But it's still the case at any time. There's some amount of the identity, some amount of sigma x, some amount of sigma y, some amount of sigma z, because that is a basis. Okay? So, given such a Hamiltonian, what can we say about the physics of it? Well, this is equivalent to a spin magnetic dipole moment in a magnetic field. So, if I have a object which has spin and charge, it will have a magnetic dipole moment. So classically, if I have a spinning ball of charge with some amount of charge Q, it has some angular momentum. It also has a magnetic dipole moment. Remember, you have current, you have magnetic dipoles, loops of current. And there's a relationship between the amount of magnetic dipole moment and the amount of angular momentum. And that proportionality constant is called the gyromagnetic ratio. And if it's a spin, it's not a spinning ball, but nonetheless, there is the same relationship between the magnetic dipole moment as if there was a current flowing and the angular momentum related to the mass that is rotating. And that ratio is called the gyromagnetic ratio. And we always call in quantum optics the magnetic dipole mu, not m as it is in Jackson, okay? So this is magnetic dipole moment, and it's proportional to the spin. And this proportionality constant is known as the gyromagnetic ratio. So when we put that all together, I can ask, what is the Hamiltonian? Well, the Hamiltonian is something which wants to align the magnetic dipole with the magnetic field. So if I put this in a magnetic field, then it wants to align with it. It has lower energy when it aligns, mu dot B, which is equal to minus gamma B dotted into minus H bar. So I wrote this as H bar over to sigma. And so a spin magnetic dipole in a magnetic field is a vector times sigma. So what we're going to do tomorrow, meaning next lecture, is remember and review, and I would ask you to go back to Griffith's E&M undergraduate textbook and remind yourself about classically, what happens if you put a spinning charge in a magnetic field? How does it go? It precesses. It's the same thing quantum mechanically, so we'll talk about that all next time, but I am over time. I'll take your questions outside, I promise. Let's erase them.